Hello, welcome to one more day. So today let's look at this very complicated picture to try to make sense of it all. So here's the story. Suppose you have two goods in the economy, apples and banana. X1 is the number of apples the consumer will have. X2 is the number of bananas the consumer will have. Each point here on this plane will indicate a bundle with a certain number of apples and a certain number of bananas. Okay? Now, this function here, the utility functions, takes each possible bundle, each point here, into a real number. It gives you the level of utility of the consumer, how happy the consumer is when he has or she has exactly that particular bundle. Okay? This function here, capital X, from the real numbers to this plane, is the parametrization of the indifference curve. So that's the red curve here, and the red curve is
the indifference curve.
Okay, very good, class. The red curve is the indifference curve. It's all the points of this plane such that you have utility exactly equals to u0, okay, for some real value u0, some level of utility. It's the inverse image of the utility from the point u0, okay? So, what we do, we compute the gradient. The gradient of the utility function is the vector made from the partial derivatives. And we also can take the derivative of this parametrization function. It's going to be a vector also in R2, 2 dimensions, where you take the derivatives of each one of the coordinate functions x1 of t and x2 of t. Okay? So the derivative of this vector function is made by the derivatives of each coordinate of this vector. Okay? So in the picture here we have a special point which I call t star. When you apply the parametrization at this point t star, we arrive to this point x star, capital X of t star, and we compute the gradient at this point x star. It's going to be orthogonal to the tangent plane. So this t of x star is the tangent hyperplane. In this case, because the dimension here is 2, this is going to be a straight line on the direction of the velocity of the parametrization. So the parametrization will be a vector along this green line, while the gradient will be orthogonal, will be 90 degrees, a right angle here. Okay? And so here we consider this constant function. This parametrization is such that the composite function between the parametrization and the utility function, picks the real numbers and takes you into real numbers. And for every value of t, as we move here, we always go to u0, because as we move the value of t here, we are always along the indifference curve. So that's why this is a parametrization of the indifference curve, because we are constructing a function x with this property that as we move along t, we are moving along this red line, the indifference curve. Okay? So then, when you apply the utility to any point of the indifference curve, you get the same level of utility, u0. Okay? So we apply then the chain rule from many variables. And this is the formula for the chain rule with many variables when you apply to a genetic point t of the domain here. When you apply to the particular point t0, what we are doing, we are taking the derivative with respect to t of both sides of this equation here. Okay? So this is the important equation. We are taking the derivative with respect to t on both sides and evaluating at t equals t star. So this is a constant. When we take the derivative with respect to a constant, we get 0. And here we have a composite function. So we have this the chain rule for multivariable functions. Okay? So this is essentially saying that the vector gradient is going to be orthogonal to this speed vector, to the x prime. So this, and because the x prime is along the tangent hyperplane, this gradient is going to be orthogonal to the tangent hyperplane. Okay? So the gradient is pointing out to the direction of maximal increment on the utility function. That is, if you are at this point here and you want to increase your utility the most, this is the direction you should be trying to go to. Okay? While if you're here and you want to keep the same level of utility, you should go along the green line. At least locally, that's what happens. So globally things can be different, we know that, but locally that's the picture of the local analysis. Maximum increment in utility, you go in this direction. If you want to minimize your utility, go the opposite direction. If you want to keep the same level of utility, you walk along the green line here, at least in the neighborhood of this point. Okay? So thanks for watching. Bye bye.